recording. So we're going to continue on here in section 10.7, which starts on page 273, and it's spur gear kinematics. And the two things on that we're going to be learning about to kind of tie these things together are going to be the velocity ratio, which is going to be abbreviated VR, and pitch line speed, which is going to be VP. So if we look underneath on page 273, we're going to see the two gears that we've looked at a couple times in engagement here. And we're going to specifically look at the angular velocity of the pinion with relationship to the angular velocity of the gear. And what's going to happen here is that gear is going to slow down, all right? Because as we look, the pinion has fewer teeth on its perimeter. So when it goes around once, it's only going to take up a section of the teeth that are on our gear. So what we want to find out is how many times does that pinion have to go around to get the gear to go around just once? And this is called velocity ratio. Okay, velocity ratio. Velocity ratio is going to be calculated using equation 1017. Okay, and when we're purely looking at the rotational speed, we're going to take the rotational speed of the pinion divided by the rotational speed of the gear. And again, when we have two gears in engagement, the pinion is going to be the smaller, faster rotating gear, and the gear is going to be the larger. So you'll notice this one's called the pinion and this one's called the gear. Okay. So the larger number is up on top. So what we're going to do is we're going to add that to our equation sheet. So I'm going to zoom out here a little bit, and I'm going to go on my equation sheet, and I'm going to add velocity ratio is equal to, okay? Velocity ratio is going to be omega 1 over omega 2. Omega 1 is going to be the angular velocity of the pinion, okay? And its units are going to be RPM or radians per second, as we know, okay? I'll bring this over here. RPM or, this isn't or, radians per second. W2 or omega 2 is going to be the angular velocity of the gear. Okay, it's going to be the larger of the two. So again, it's going to be RPMs or radians per second. Okay, this is an RPM. Totally backwards. There we go. Okay. Now, VR, capital V, capital R, is velocity ratio, sometimes referred to as what's the gear ratio, right? Do you guys ever hear that? What's the gear ratio between those two gears? And it tells us how many times the pinion has to go around in order to get the gear to go around just once. Okay, that does not have to be an integer number. Sometimes you might say it's 2-to-1 ratio or a 3-to-1 ratio, but it can be a decimal as well. It doesn't have to be an integer. Okay. Now, not only can we calculate velocity ratio using the angular velocities of the pinion and the gear, we can also determine it by the physical attributes. So if we look up here, equation 1019, we have velocity ratio equal to, notice we have the angular velocities here as the first, the omega 1 divided by omega 2. But then we've got the radiuses, the diameters, and we can use the number of teeth. Something you want to note about the arrangement here, though. Notice that it's always the larger number on top. So when we're looking at rotational speed, the faster moving gear is the pinion, okay? Because think of that as coming off a motor, all right? And then the slower one is going to be the gear, the larger gear. But when we start looking at physical sizes, notice that the 2's go on top now because the gear is larger in radius, the gear is larger in diameter, and the gear has more teeth. So on the tops for the physical attributes, the gear would go on top divided by the pinion. Does that make sense to everybody? Okay, so we can add to that equation by saying equal to radius 2 over radius 1 equal to diameter 2 over diameter 1, which is equal to the number of teeth on 2, number of teeth on 1. Okay, and again, 1 equals pinion and 2 equals gear. Okay. Just a little star. We already have N's and D's and R's identified on the side, so we don't need to re-put those in. Okay. Nope. Again, it's because we need the larger on the top. When it's the rotational speed, the 1 stays on top because remember, that's coming off your motor. So that's going to be like 1750, and then you want the lower speed on the bottom. But then when the physical size, the gears are larger in physical size. So the radiuses, the diameters, and the number of teeth would be gears on the top. So no, 2's go on the top for the physical attributes, and then the number 1 goes on top for the angular velocity. Okay. All right. Always the larger on the top. Okay. Now, the other element that we're going to be interested in when we look at gear kinematics is not only how fast these are rotating relative to one another, but how fast is the straight line velocity component or the pitch line speed. So that is going to be our variable VP, and it's going to be the magnitude of the velocity of the pitch point of the 2 mating gears. Okay, VP is going to be the same number for both gears. So if we go back to, too far here. Oh yeah, we go back to page 273 underneath here, and we look at this illustration again, you're going to notice that we have this vector. Okay, and this vector is pointing down, and it's V sub T or V sub P, the pitch line speed. Okay, the pitch line speed. So what that is when we look at the outermost radius of the pitch diameter, and we're rotating in this case, a clockwise direction on our pinion, the straight line velocity component of that circular motion is going to go perpendicular to the radius in the direction of rotation. Okay. Now that same pitch line speed is not only going to be the same on the pinion, but it's going to be the same on the gear. In the case of the pinion, we're going to have a higher speed with a shorter radius. In the case of the gear, it's going to be a slower speed, but a larger radius. And this equation is going to be familiar. This equation is going to be at the top of page 274, where pitch line speed is going to be equal to the radius times the rotational speed of either the pinion or the gear. So we can add that to our list. So pitch line speed, V, and we'll do it sub T, I think is what they're using in this example coming up, is going to be equal to R1 times omega 1, which is also equal to R2 times omega 2, where again, the pinions are the 1s and the gears are the 2s. VT is pitch line speed. And it is going to be in inches per second. Okay, inches per second. Pitch line speed is the same as the straight line velocity component of the rotational motion. Kind of like when we had VB, VC on our links. And then the radius and the rotational speed. Now in this equation, that rotational speed has to be in radians per second, okay? We have to use radians per second in this equation, just like we did in our previous modules. Okay. All right. So now we're ready to look at example 10.8. Example 10.8 is on page 274. Okay, pull this here. And let's look at the problem statement to start off with. Okay. So it says here we have a set of gears, they're right down here, to be used to reduce the speed of an electric motor to the shaft driving a grocery checkout conveyor. Okay. The gear on the motor shaft is a 10-pitch pinion, has 15 teeth, and drives at 1800 RPMs clockwise. Determine the speed of the mating gear, which has 45 teeth. Also calculate the pitch line speed. Okay. So what I want you to do is, in this description here, pull out as many known variables as you can based on your gear equation sheet. Okay. So see if you can find a diametral pitch, number of teeth, pitch diameter, W's, C's if they're there. Okay. And then, identify them for your problem. And we'll go through that together. I want to give you a minute to write those down. What are the things that are given here? What are the things that are given? As we read our problem here, okay, I'm going to kind of get started. It says we have a set of gears, electric motor, grocery checkout conveyor. So our input is going to be that motor, right? Our output is going to be the conveyor, the grocery conveyor. So it says a gear is on the motor shaft. It's a 10-pitch pinion. What is my variable that 10 pitch identifies? What is it? 10 feet. What'd you say? Feet? No, 10 teeth per inch. So what is that called? Look on your thing. Look on your thing. What is that called?
Diametric pitch.
Diametral pitch. Don't say diametric. Don't say diametrical.
Sorry.
It's diametral. No, that's okay. That's okay. It's getting used to the terminology. So diametral pitch. Diametral pitch. So that's going to be capital P sub D is equal to 10. And the units for that are teeth per inch. Now, even though they don't give it to us, we want to expand that out because we need to put those in our equations. So that's diametral pitch. Good. It says it has a 15 teeth on the pinion. So what variable is the 15 teeth? What is it? Yep, capital N sub 1, right? The number of teeth on the pinion, capital N sub 1, and that is 15 teeth. Okay. It tells us that pinion drives at 1800 RPMs. What is the variable for that 1800 RPMs?
Omega 1.
Omega 1, absolutely. So, or W1 omega 1. So omega 1 is equal to 1800 RPMs. Okay, good. And then it wants us to determine the speed of the mating gear, which has 45 teeth. So what is the 45 teeth? What variable will that be? N2. Yep. So that's a given. N2 is 45 teeth. Okay. And then it said that we need to find or determine the speed of the mating gear. What variable would be the speed of the mating gear?
Omega two.
again. Yep, omega 2, thank you, is what we need to find. Okay. All right. So if we look at our equation sheet, right? Omega 2 is what we want to find, and we're given omega 1, right? We're also given number of teeth, diametral pitch of our gears that are in engagement with one another. So as we look here, and we want to find, oh, the other thing we want to find, I'm sorry, there's another thing. It says also calculate pitch line speed. What variable is that? Yep, that VT, yep, we want to find that. Or P, either one. Okay. So for the speed of the gear, as we look here, we want to look, where do we see W2? Okay. We see W2 here in the velocity ratio, right? And then we also see it down here. Okay. Down here at the bottom, this is in terms of pitch line speed, right? So technically, we need to have our W2 or our W1 before we get that, right? But up here, we have our W2 and our W1, okay? We also have the number of teeth here. So we can set W1 and W2, or W1 over W2, equal to N2 over N1. And we're going to find our W2 will be our only unknown, okay? So that's one way that we can use that. So let's go ahead and use that relationship to find W2. So we can say that W1 over W2 is equal to N2 over N1, okay? Again, all of these are equal to one another. Not only can we calculate the velocity ratio, but we can set these equal to each other and solve for unknown variables. So in this case, we know what W1 is, right? 1800 RPMs. We know what N2 is, 45 teeth. We know what N15 or what N1 is, 15 teeth. So our only unknown is W2. Okay. So go ahead and rearrange to solve for W2. Okay. You guys get the same thing? W1 times N1 divided by N2. Yep. So now we can plug in our values. 1800 RPMs. This one we can leave it as RPMs. We don't have to change it to radians because this is just a ratio. N1 is 15 teeth. N2 is 45 teeth. The teeth cancel out. And our W2, what do we get? What do we get for our W2? Anybody get a number yet? 600 what? RPMs, exactly. So W2 is equal to 600 RPMs. Now, when we were given the 1800 RPMs, the direction was clockwise, right? So what is the direction of W2? Counterclockwise. Remember, when we have two gears in engagement with one another, the rotation of the one gear to the next is going to be opposite. So this is going to be counterclockwise, okay? Then now that we know the rotational speed here, that takes care of W2, we need to find the pitch line speed. So number 2, pitch line speed, VT or VP, equal the same thing. It's going to be the radius times the rotational speed of one of the gears, okay? Now, when we look at the gears here, rotational speed-wise, we were given the 1800 for W1. So for the pinion, I'm going to use the pinion then to calculate this value. So I know this needs to be R1 times omega 1. Now, the radius is going to be half of the pitch diameter, okay? Remember, when we look at the relationship here, we need to find the radius of the pinion, okay? And that's going to be the radius to the pitch line, okay? Where that velocity is, that's going to, in this case, go down, okay? So I need to know what the diameter is divided by 2 of that pinion, all right? To calculate that, I'm going to use that relationship of the diametral pitch is equal to the number of teeth divided by the pitch diameter. So solving for the pitch diameter of the pinion, okay, to find the radius here, I'm going to say D1 is equal to N1 divided by the diametral pitch. Okay, it's just rearranging that equation. That's going to be equal to 15 teeth divided by 10 teeth per inch. The teeth cancel. I'm left with inches in the denominator of the denominator. So my D1 is going to be 1.5 inches is equal to D1. This is not a final answer, but I'm going to use it to get my radius here. And then my W1. My W1 in this equation has to be in radians per second. Okay, I can't have it in RPMs. So my W1, which is equal to 1800 revolutions per minute, I'm going to convert that to radians, 2 pi radians, sorry. And then 1 minute, 60 seconds, right? My W1 is going to be 188.5. Is that what you guys got? Okay.
Yep.
Equal to W1. Thank you. Okay. And now these two values we're going to use in that pitch line speed. So VT is going to be equal to D1 divided by 2 times W1 in radians per second. So this is going to be 1.5 inches divided by 2 times 188.5 radians per second. Okay. My pitch line speed is going to be you get 141.4 inches per second, right? Is equal to VT. This gets a box around it. There we go. Okay. And if you peek at the answer, they have it in per minute, which is a very common value. So I'm gonna have to convert mine on the next page. So 141.4 inches per second. If you have room, go ahead and add yours. So 141.4 inches per second. And we just want to convert that to feet per minute. So there are 12 inches in 1 foot, and there are 60 seconds in 1 minute. So my V sub T 706.8 feet per minute. Inches cancel, seconds cancel. And that is, they got 706.9. So, Jacob. Oh, okay. Yeah, did you guys also get that? Hopefully. Okay. So that's our pitch line speed, 706.8 feet per minute. So that would take care of the second part of that problem. So there you go. Example 10.8. Any questions on that one? Dylan? Where did the 2 come from? Oh, so the radius is what you need for multiplying times the angular velocity in radians per second. So we had the diameter. We calculated the diameter of 1.5. So we had to divide it by 2 to get the radius. Yep, that's where that is. Good. Any other questions? All right. Then we'll go back to our PowerPoint and go to the next section here. So our next section is gear selection. So part of what the designer is going to do, a designer needs to specify what are the gears for an application. And when they do so, we have to be sure that we have 3 common parameters between them. First things first, we have to actually 2 common parameters, but then we have to specify a third. So the first one is going to be the diametral pitch. Remember, the diametral pitch is the size of the tooth. That has to be the same for 2 gears that are in mesh. The other thing that has to be the same is the pressure angle. Like I said, we always start with 20 as long as that works okay. 25 is another option, but only in cases where we need to get the stress for bending that tooth over down. Okay, but most of the time 20 degree is what we're going to use. So those 2 have to be the same between 2 gears that are going to be in mesh. Then the third parameter that we would provide as far as specifying a gear are the number of teeth on each one of the gears. Now that's going to be different, but the number of teeth has to be an integer. Okay, has to be an integer. Now, as we look at diametral pitch, as we know, is the size of the tooth. It's always going to be the first parameter that we select. Okay, and it's going to be based on 2 variables. Okay, and those 2 variables are going to be here in table 10.6 on page 275. We are going to base the diametral pitch on the pinion RPM, the faster of the 2 gears in mesh, and the amount of horsepower that we're going to be pushing through that set. Okay. What you're going to notice is that the numbers get smaller as we move down this chart. And remember, the smaller the number, the bigger, the chunkier the tooth. So at the beginning of our chapter, we had the illustration on page 263. And this is where we have common diametral pitches. And we'll notice that these are those standard, if you would, categories of size of teeth. And the larger the number, the smaller the tooth. The larger the tooth, the smaller the number. Okay. So as we work down and we push more horsepower through, notice that our teeth get bigger and bigger and bigger. Okay. Up at the top here, they're smaller. And I know that because the diametral pitches are larger numbers. Okay. So what we do is we find our pinion RPM, our power, and when we put those 2 together. So for instance, if we have 1800 RPMs and we're running 1 horsepower through, we would have a diametral pitch of 20. This is a place to start. Okay. That doesn't mean that once we figure out the forces and the stresses, if the stresses and the forces are too high, then we have to make it a larger tooth or a smaller diametral pitch. Does that make sense? Okay. So this is always a place to start, because sometimes you might be like, I have an application, but what size tooth should I use? Here's where you can get some guidance. Okay. A place to start. Okay. So we're going to be picking that diametral pitch. Once we pick our diametral pitch, you'll notice on page 276 starts a chart. Okay, and this chart is the number of teeth for commercially available stock gears. Now, as you read this chart starts on the bottom of page 276 and it continues to the top of page 277. What you'll notice is that there are categories of diametral pitches here. So for instance, at the top, it's 16, then 12, then 10, and the numbers listed in here are the available standard number of teeth on a gear that is a diametral pitch of 16, the standard number of teeth on a gear that is a diametral pitch of 12, and so on. Now, what this means is if I would go to a gear manufacturer's catalog, And I would look up on in their gear catalog, diametral pitch of 10. They are going to have listed gears that have these standard numbers. Again, these are numbers that are, if you would, overseen by the American Gear Manufacturers Association. Okay, so these numbers will be readily available. Some manufacturers might have more gears because they might be like, hey, we have more gears that we create in this product line, but they have to make these. If they say they're making a diametral pitch of 12, then a diametral pitch of 12 from another manufacturer is going to make these same numbers as well. Okay. Now, what we're going to notice is we see, for instance, diametral pitch of 12, 12, 13, 14, 15, 16, but they skip 17. And then they go to 18. And they go to 20, 21, 24. And you might say, well, how come they skip? I'm going to tell you, I don't know. I don't know. Okay. They just do. It's kind of like, other standard elements. Okay. Why do they, choose certain belt sizes? I don't know. Why do they choose certain number of teeth on sprockets for chain drives? I don't know. Okay. So these are going to be the standard. So when we are specifying a set of gears, we, number one, need to choose our diametral pitch. And then when we pick our number of teeth, it has to be on the list. We can't pick a random number. Okay. So we're going to be, going through some problems where we choose the number of teeth, based on the commercially available ones. Yep. 10-6. We talked about pressure angle already, and knowing that there has to be the same between gears that are in mesh. And then we just talked about number of teeth using table 10-7 to specify the most common commercially available type number of teeth on a gear. So now what we're going to do is we're going to do example problem 10-9 and then 10-10, and those will be the last two problems that we work in this part one of module 6. So if we go to the top of page 276, we're going to find problem number 10-9. Okay. 10-9 says a pair of mild steel gears to be selected for that concrete mixer described in the previous example. The mixer is driven by a 10 horsepower engine at a speed of 1800 RPM. Determine the appropriate diametral pitch. Okay, so we're going to go back to that table 10-6, okay, on the previous page. And what we're going to do is we're going to find 1800 RPMs on that pinion, and we're going to go down to 10 horsepower. Okay, so 10 horsepower is right here, and then 1800 is down this column. And you're going to notice that it comes together and it specifies a diametral pitch of 8. That's it. Okay, so what we're going to do for this simple, short example, we're simply going to list example 10-9 and PD equals 8 per table 10-6 on page 275, right? Yep. And that's it. Okay. Then we're done with example 10-9. Easy peasy. So it's just practicing using that chart. That's it. So diametral pitch of 8 per the table 10-6 on page 275. Okay. That's all you have to write for that one. Okay. Now the other example we're going to go through is going to be example 10-10. Okay. So let's look at the description for example 10-10. So in this case, we have a gear reducer is used on a concept for a small trolling motor for fishing boats. The gear must transmit 5 horsepower from an electric motor at 900 RPMs to the propeller at 320 RPMs. Select a set of gears to accomplish this task. Okay, so this is going to be problem 10-10. So I'm just going to go right down below here. So example 10, 10. And what we're given here is that our horsepower equals 5 HP, okay, 5 horsepower. Our W1 coming off of our electric motor is 900 RPMs. And the propeller W2 needs to be at 320 RPMs. Okay. We want to select a set of gears. So select gears. So to select gears, we're going to have to find the diametral pitch. Okay, that's going to be common between the two. We're going to have to specify the pressure angle, the number of teeth on the pinion, the number of teeth on the gear. And then they also are going to be determining the center distance. Okay. Okay. All right. So first things first, we're going to pick that diametral pitch and we're going to use table 10.6 again. So for our problem, we're going to use the pinion, which is the faster moving shaft. Okay, so that's going to be our W1 and our horsepower. Okay, so if we go back to table 10.6, we're going to find the 900 RPMs, right? And we're going to find 5 horsepower. So it looks like we come together at a diametral pitch of 10. Do you guys see that? Okay. So that's the first element. Okay. 1. P sub D equals 10. And I'm just going to put per table 10.6. Okay. That's it. Pressure angle. All right. Pressure angle. Now, we're simply going to look back at that table 10.6. And since we used this to determine our diametral pitch, notice at the top here, this is for 20-degree pressure angles. Okay. So that means that number 2, PA, is equal to 20 degrees. And again, it's going to be per table 10.6. Not 20%, 20 degrees. All right. So that one's done. Diametral pitch and pressure angle. The next one is going to be our number of teeth in our pinion and the number of teeth in our gear. Now, these two, they have to come from the standard list. Okay, they have to, so we have to find, if you would, 2 gears that are going to give us 900 to 320 RPMs. Okay, 900 to 320 RPMs. So what we're going to do is we are going to use the velocity ratio relationship to help us with this. Okay, so we want to calculate the velocity ratio that we need to go from 900 to 320 RPMs. So that velocity ratio is going to be W1 divided by W2. So we're going to put our 900 RPMs on top and 320 RPMs on the bottom. RPMs cancel. And what do you get for a velocity ratio? Do you get 2.8125?
Yep.
Yep. Okay. So 2.8125, okay, is going to be our velocity ratio. Now, if we know that that's our velocity ratio, okay, and we look back at the equations we have for velocity ratio, not only can we calculate using our angular velocities, but we can set that velocity ratio equal to N2 over N1, okay? So I am going to go to my next page here. Okay. I am going to say my velocity ratio is equal to N2 over N1. Okay. I know my velocity ratio. Okay. If I rearrange this to put one variable on one side and one on the other, I can say N1 times 2.8125, right? That's that variable or that velocity ratio equal to the number of teeth on my gear. So number of teeth on my pinion, number of teeth on my gear on two sides of my equation. All I did was rearrange this, multiplied N1 up. Okay. Now what I want to do is I want to open my book to the section where I see diametral pitches of 10. And I'm going to use these numbers to see if I can find a set that gives me exactly two values that come out for me. So I'm going to start here with N1 is equal to 14. Okay. All right. N1 is equal to 14. So that means I'm going to take 14 teeth times 2.8125, and I'm going to calculate what N2 is going to be. Okay. So what do you get for a value of N2? Bless you. Do you get a value of 39.375? Yeah. So if we look at our list of availables, do we see 39.375? No. And just the fact that we got a decimal number is not going to work for us. We have to get exactly 320, so we've got to get an integer number. So that means that N1 at 14 is not going to work. Okay. So then we're going to do the same thing. We're going to go to our next number. We're going to say, okay, if 14 doesn't work, maybe 15 will work. Okay. It's on the list. So I'm going to say, okay, N1 is equal to 15. Okay. So I'm going to take 15 teeth times 2.8125 is equal to N2. And what do we get for N2? Yeah. So the 0.1875 means that 15 is not going to work either, right? Let's try 16, because I think 16 is next, right? Yep, we go from 15 up to 16. So we'll try 16. So we're going to say N1 is equal to 16. So we're going to take our 16 teeth times 2.8125 is equal to N2. What do we get for N2? 45 teeth. Ooh, that's an integer number. Let's see, is there 45 on our list? So we've got 16. Oh, and we've got, sorry, and we've got 45. That's a good pair. Okay, so that means that this, our N1 is equal to 16, and our N2 is going to equal to 45. And that's teeth and teeth. Okay. So that's a good pair that is commercially available, standard sizes. Okay. And why would you imagine we would want to work off of a list like that is the standard sizes? Like if I opened up a catalog even, I would want to work with the number of teeth that are there. Why would I want to do that?
So that it's not more expensive to get one with a custom set of teeth.
Yeah, custom will always be more expensive. And then Dylan also said it's going to be faster, right? Because they're going to be off the shelf. So those are two great reasons. Cost and availability are going to be what you want to go with. Now, does that mean that you can't get a custom tooth? No, you probably can. It's just that you're going to spend more and it's going to take more time to get there, right? So whenever we can, we want to work off the commercially available list. All right, so if we look back at things that we need to find, we just got N1 and N2. So the last thing we need to calculate is going to be our center distance, okay? Our center distance. So if we pull out our equation sheet here, we have two options for center distance. We have the diameters, or we have the number of teeth and diametral pitch. I'm thinking the second one is going to be the fastest to get to our center distance, okay? So let's use that second equation to calculate our center distance. So this one is going to be C is equal to N1 plus N2 divided by 2 times the diametral pitch. So go ahead and use the numbers that we just found. So it's going to be 16 and 45 for our number of teeth. Divided by 2 times the diametral pitch of 10, which is teeth per inch. So teeth cancel out top to bottom. So our center distance did you get 3.05? Yep, and that should be, yep, good, 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 good. And that takes care of our last variable. Okay. So we identified the size of the teeth, which was a diametral pitch of 10, the pressure angle, 20 degrees. We found the number of teeth in the pinion and the gear that would accomplish the 900 to 320 speed reduction, and that was 16 and 45. And then finally, the center distance physically, how far apart is the center from the pinion to the gear? That's 3.05 inches. Okay. All right. Any questions on that example? Okay. Okay. All right. So then if we look at our PowerPoint presentation, that brings us to the end of our part 1 for module 6 here. So the next time that we get together, we're going to look at gear trains, and that's when we actually have sets of gears that are going to be together, kind of string together, if you would. So before I let you go, let's take a peek at first our practice problems we have. So we have gone through, it looks like the first 5 practice problems. We did 10, 10, and then the next time we get together, we have 2 more that we're going to do, okay? And then if I look at my assignment, we are going to be able to do, or I shouldn't say we, you are going to be able to do all of the problems through 1025 that are on our list here with the stuff that we did this evening. Now, I want to call your attention to the first couple here. So if we open up to the end of the chapter, okay, if we look at 10.5 and 10.6, notice you're only doing part A. So if I look underneath here, 10.5 and 10.6, you're only finding the center distance for those 2 problems. You're not doing the rest of this, okay? So only the center distance. Then for the next 3 problems, 9, 13, and 14, they're referencing internal gears for the problem. Cross out internal, and they are all going to be external gears, okay? Makes sense. And external just means they have the teeth on the outside perimeter of the gear rather than internally, okay? So change internal to external for each one of these. So you'll notice on the problem statement as well, for 9, 13, and 14, both external gears. Do not do internals. And then the other ones, they're as stated, okay? So again, you can do all the way through 1026 up until the last 2 problems, and everything that we covered this evening will get you that far. You'll notice that there are answers here to these, problems. So you can check the answer key to see how you're doing. But that's all that I have for this evening. So, so the rest of the time is going to be yours to use for lab to ask questions and work if you need to. And then otherwise, I'll be all set. Now, I'm going to stop recording.